Most of the current mainstream programming languages treat strings as UTF-8 encoded. To understand how strings are implemented or processed and their relation with byte arrays in your programming languages of choice, it's better to first understand a few basic concepts like Grapheme, Unicode, and different types of encodings like ASCII and UTF-8. This video intends to cover the minimum amount of information developers must know about these topics. In the initial days, the ASCII had a code corresponding to each character. The ASCII codes were from 0 to 127, a total of 128 items. The first column in the table shows the ASCII code in the decimal number system and the second column shows the actual character. The ASCII codes from 0 to 31 are used to represent control characters. Codes from 48 to 57 represent the numbers from 0 to 9, 65 to 90 represent English uppercase letters, and 97 to 122 represent English lowercase letters. In many programming languages, the backslash is used as an escape character, to indicate that the character following it should be treated specially. You might be familiar with \T for tab or \N for new lines. Similarly, the \_ corresponds to ASCII code 7, which when output to a supported terminal, will produce a bell sound. Not all terminals produce the sound, it's up to the terminal how to treat these codes. The \B corresponds to ASCII code 8 that represents backspace. So, the output of the second line will not contain the character C because of a backspace after that. Also, these are not specific to any programming language. It's up to the output device, which in this case is a terminal, how to interpret these control codes. Since there are only 128 codes in ASCII, all these characters could be represented using 7 bits. We don't deal with bits directly, so a single byte is used to store an ASCII character. This process of converting something to its storable binary representation is called encoding. Here, each character in the string is mapped to its corresponding ASCII code, and then the binary representation for each of those ASCII code is generated. Each of those letters fit into a single byte. The reverse process is called decoding, where we retrieve the string from its binary representation. The ASCII codes worked in the early days since the initial computers were created in English-speaking countries. But when other countries started adopting computers, the ASCII codes couldn't be used to represent characters in their languages. This is when the Unicode standard was created. In linguistics, the word grapheme is used instead of character. This is because the word character can be ambiguous, and it can mean many things. A grapheme is a graphical unit that a reader recognizes as a single element of the human writing system. These are examples of graphemes where each one is an English, Hindi, Chinese letter and an emoji. Just like ASCII, each of these graphemes has some code points defined in the Unicode standard. The Unicode standard can also represent emojis. The Unicode value shown here is in the decimal number system. Each code point is a number that is given meaning by the Unicode standard. All these graphemes are represented using single Unicode points. Some graphemes are represented using multiple Unicode points. For example, the colored version of the thumbs up emoji is represented using 2 Unicode points, one corresponding to the regular emoji and the other for the color. Similarly, this Latin small letter E with acute can be represented either using a single Unicode point or using a combination of 2. Notice that 101 is the Unicode point for the Latin small letter E and the other code point is the acute accent modifier. So, in summary, both ASCII and Unicode standard has unique codes for the graphemes it represents. In ASCII, we only had 128 codes, whereas the Unicode standard specifies mapping for around 144K characters. Also, note that the codes for characters specified in ASCII remain the same in the Unicode specification. Just like we saw, Unicode also specifies how to combine characters. Unicode also specifies the direction of the text for languages that read from left to right or right to left or top to bottom. Computers store and transfer data as binary. Converting the graphemes to binary is called encoding. In ASCII, this was simple, since all code can be represented with 7 bits, we use 1 byte to store any code in the ASCII table. However, since Unicode has a much larger range of values, a single byte is not enough. There are multiple encoding schemes for Unicode. Each has its advantages and disadvantages. Each encoding uses different byte sequences to represent Unicode values. For example, UTF-32 is one such encoding scheme for Unicode. It uses 4 bytes to represent every grapheme. The advantage of this encoding is that all graphemes will take fixed 4 bytes. Identifying the position of each grapheme in a string is easy. The disadvantage is that it wastes a lot of space. As I already mentioned, the code for letters specified in ASCII has the same value in Unicode. The 5-letter word hello will only take 5 bytes in ASCII. However, it takes 20 bytes in UTF-32 encoding, which is 4 times that of ASCII. As you can see, 3 bytes in each letter is a waste of space. This has a higher impact since the lower-end Unicode like English letters are used more often. For example, think of a website with contents in Hindi or Chinese. Its building components like HTML, CSS, and JavaScript uses English keywords and is likely to be more than the content itself in terms of the number of characters. UTF-8 is the most popular encoding for Unicode code points. UTF-8 is a variable length encoding. In UTF-8 encoding, the first 128 code points require only 1 byte. The next 1920 code points between 80 and 7FF need 2 bytes to encode. UTF-8 uses specific patterns in the first few bits to determine how many bytes are used to represent a grapheme. For Unicode points between 80 and 7FF, the first byte will start with the bit pattern 110 and the next byte will start with the bit pattern 10. You should be able to read and understand the rest of the table now. With UTF-8 encoding, the first 128 code points require only 1 byte and thus have the same representation as that of ASCII. The downside of UTF-8 is that code points have unequal sizes in bytes, which makes it harder to index the letters in a string. Let's see how different programming languages treat strings. By seeing the implementations in different languages, you will understand how similar they are. There will be small differences based on design decisions in each language. First, we will look at some Golang code. The string in this code has 4 letters or graphemes. If you use the built-in range loop, Go iterates over individual Unicode code points. So the index is not continuous since Go assumes string constants are UTF-8 encoded. The first letter only takes 1 byte, and the second and the third letters take 3 bytes each. If you try to index a string, Go indexes the underlying byte array and it shows the Unicode character corresponding to the byte at that index. This might not be the actual letter or grapheme at that index since UTF-8 encoding might use more than 1 byte to represent a letter. Python treats strings as UTF-8 encoded. Unlike Go, if you iterate over a string, Python will iterate over each letter and treat its index positions as continuous. Even if you index them directly, it returns the grapheme at that point and doesn't do indexing over the underlying bytes as it was in Go. You can view the binary representation by encoding the string. The default encoding is UTF-8. But other encoding types are also supported. As we discussed, we can see that encoding the same string as UTF-32 takes much more space. If you had to decode a byte array to a string, you need to know what kind of encoding is used to generate that byte array. For example, if you had an array of bytes which are UTF-32 encoded, and you try to construct a string from it by decoding it as UTF-8, it will fail. The Rust programming language makes the iteration explicit. You need to specify whether you need to iterate over individual letters or bytes. Note that even though I mentioned all these languages provide ways to get individual letters in a string, there is a catch in that. In all these languages, wherever I mentioned they are returning a letter, it's not exactly a letter or character. It's a Unicode value. It works as expected if the letter is represented using one Unicode point. But we saw that some letters use more than one Unicode point. One such example is this letter. Even though it's a single letter or grapheme, it is represented using two Unicode points, and all three languages, Go, Rust, and Python, shows them as consisting of two characters.